Okay, so I suggest to kick off this session. So welcome everyone to Machine Learning in Macroeconomics. So my name is Andreas Joseph. I'm a research economist at the Bank of England. And today I think are tackling a quite kind of challenging subject in terms of machine learning and macroeconomics. Because I think it's on the one hand very interesting, on the other hand very challenging, because macro has quite few data traditionally, and today we will see like how this, which is very challenging for machine learning in general, and how this can be addressed with a set of interesting problems, looking at wealth inequality, some technical properties of machine learning, and then a forecasting exercise. So just some words for organization. So each speaker has 20 minutes and then followed by 10 minutes this Q&A. I will take time and I will tell all speakers when there's 5 minutes left, and then when the time's up, and then we see how much time we need for Q&A. Finally, this, just for information, the session is being recorded. And then without further ado, I hand over to Pedro. So thanks everyone for joining. Thanks for the organizers, and let's have a good and interesting and fun session.
Thank you, Andreas. Now I'm supposed to be sharing my screen. I hope so. Am I?
Yes.
Okay.
I can see it.
Well, hello everyone. Thank you for coming by. My name is Pedro Salas, and first of all, I would like to express my acknowledge to the organization of the Congress that allowed me to present this little paper that I have done with Juan Gabriel Rodriguez from Complutense University, in which we relate the inheritances and wealth inequality. And for that task, we use some machine learning algorithms, really basic machine learning techniques. So let's go directly. This is the main layout of the presentation. So let's go directly to the introduction of the topic. Many factors so far has been blamed for the persistent increase in total inequality that many Western societies have experienced in the last decades. And some authors say, okay, this is due to financial knowledge disparities. There are some guys that are able to invest better than the others because they have more skills or whatever, so they can accumulate more financial, particularly more financial wealth, so this increases wealth inequality. Others, such as Stockman, they say that it is provoked by the decline in progressive taxation. So we have like many different explanations, potential explanations. But okay, what is the role of inheritances? Because of course, inheritances are the way in which wealth or the stocks are transmitted across generations. And we have found that while some part of the literature says that inheritance are actually the main vehicle through which these inequalities in wealth are transmitted and are even increased through generations, other part of the literature says that, okay, inheritances are actually more equally distributed than wealth. So when this intergenerational transfer is performed, the net result decreases overall inequality. So we find that this variable, which is supposed to be like the main horse battle for the analysis of wealth inequality, have these confronting results. So what do we do in this paper? What is this paper about? We assess the relation between inheritances and wealth, but from a different perspective. We analyze it from the inequality of opportunity literature. So we propose some really basic machine learning algorithms, that we use them, that deal with some traditional limitation of this literature. And then we measure in this way the share of overall inequality that can be attributed, that can be collected into the inheritances. And finally, we employ single parameter genies that study the impact of inheritances along the wealth distribution. So let's go directly to the methods. First of all, I will introduce an inequality of opportunity framework. We know that any economic outcome, such as wealth, income, or health, are actually a function of two kinds of variables. First of all, we have circumstances, which are factors beyond individuals' control. For instance, gender or race or the parental education or the inheritances. I mean, they are beyond your scope. And on the other hand, we have efforts which are chosen by the individuals. For instance, the number of hours worked or studied or whatever. In this sense, overall inequality can be decomposed as a sum of two terms. In the one hand, we have inequality of opportunity, which is attributed or is provoked by these circumstances. And we also have inequality of effort, which is provoked precisely by the performance of the individuals. We know that the first component, the inequality of opportunity component, is undesirable, not only for social justice matters, but also because it hinders economic growth in the sense that it produces an efficient human capital allocation. So what's the next step? This is the general framework. So how can we measure inequality of opportunity? Okay, we know that according to individual circumstances, such as race or gender, any population can actually be divided into exhaustive and mutually exclusive groups that we call types. So a society will have equal opportunities if for a given outcome variable W, in this case wealth, and two different types, the distribution of the outcome variable of wealth in this case is the same across type. This is, we have equality of opportunity if the two types are generated by gender, if the wealth in men is the same as the wealth in women, this distribution. However, we cannot compare directly these distributions because they can cross. So this chart usually follows Van de Gaar, and then we say that a society has equal opportunities if the expected wealth or the expected outcome condition on the type is the same across all types. Otherwise, if this condition expected wealth are not the same, then we say we have inequality of opportunity. So now we know that overall inequality can actually be decomposed into inequality of opportunity, which is inequality between types, and inequality of efforts, which is inequality within types. So what do we do in this paper? We follow the inequality of opportunity literature. And then we take inheritances as our main circumstance and use it to build types. So we can measure the part of total wealth inequality that can be attributed to bequests. We split that inequality in two terms. So what is the problem here? Well, first of all, inequality of opportunity is provoked by inheritances, and we have a residual in which we have the effect of other circumstances that we cannot control for because we don't have the data, and inequality of efforts. So what is the problem here? This construction of types is quite easy if we have categorical circumstances or variables, for instance, gender or race or the parental education. But what is the problem when what happens when we have a continuous circumstance, a continuous variable as the inheritances? We have this problem. If we show in the paper, but I will not deep into that, we can discuss that later, that if we generate types based on a discretionary partition under the researcher's criteria, all results are inconsistent and arbitrary. So we can actually, we could actually modify the effects of the inheritance on wealth of this decomposition if we perform a particular partition. You can find inheritances which are highly skewed to the right. It is not the same to partition it in the median or interciles or quartiles or whatever. So we really need a way to systematize this generation of types, in this particular case with a continuous circumstance. So one possible solution is precisely to use two simple machine learning algorithms. We test some others in the paper, but now I'm going to focus just on conditional inference trees and forests. And I'm not going to deep into that because I don't have time. Just the main ideas. These algorithms, you know, that they are able to divide the complete populations, all observations, into exhaustive and mutually exclusive groups, which in the inequality of opportunity literature, they are types. And these types are not created under the researcher's criteria, but they are data-driven based on some statistical properties that, in this case, the dependent variable, which is wealth in our paper, has condition on a set of factors, on, in this case, circumstances, the inheritances. So once this partition is done, we generate several different types, and this algorithm assigns each observation with the expected outcome, which is precisely the way in which we have measured inequality of opportunity in the previous slide. So just to have an idea, this is an example of a tree. We have in the top, we have the first node, the first partition of the bequest or inheritances, and it splits the population in two, and we see subsequent partitions, subsequent nodes. So in the end, at the bottom of this tree, we have 6 little boxes. These boxes are the nodes in which we have normalized the expected outcome to 1 just to show the results, and also we find the population share that is inside that type. So if we computed inequality, for instance, with Gini or the mean logarithmic deviation, in these types, in these little boxes, we'll have an absolute measure of inequality of opportunity. If we divide that absolute measure by the total inequality, we have the share of total inequality that can be attributed to circumstances. In this paper, our main results are going to be based on the random forest because trees can be really data-driven. The results with the randoms and with the trees are quite similar. We have also tried boosted and everything. Our results are robust, but I will present here those from the random forest, which are the bootstrap version of trees, just to simplify the explanation. The data we use comes from the Luxembourg Fuel Survey, and in particular, we are focusing or we are analyzing 4 different countries: Canada, Italy, Spain, and the US. We analyzed 3 different wealth definitions: real estates, which is mainly composed by houses; financial wealth, in which we have deposits, cash, financial stocks, listed shares, and etc. And finally, we have total wealth, which is just the sum of the other 2. Of course, in this paper, we control by age and gender, because we want to avoid the effects of like cycle that might be related first to the wealth accumulation and then to the inheritances received, which are of course highly based on age. So first, let's find some really basic summary statistics. We find that the United States is the richest country in our sample, and of course the most unequal. The Gini is always above 80 points, which is the Gini index is really basic, from 0 total equality to one individual that has everything and the rest has nothing. So inequality is quite high in the United States. We find that, on the other hand, the European countries have lower wealth levels and also lower levels of inequality, always the Gini at around 60 points. And finally, Canada, which is somewhere in between Europe and the United States. So this is just to have an idea of the different countries. And let's go directly to the main results. So just a brief sum up. When we use these machine learning algorithms, particularly I say the random forests, to create these types and then attribute each individual with its expected wealth, we compute a between type inequality. We apply inequality over that vector that we obtain and obtain the share of overall inequality that we measure with Gini, although we always use several inequality index to test the robustness of our results. But here I'm going to focus on Gini. That can be attributed, the share that can be attributed to inheritances. So how can we read this table? We find that in Spain, from the total wealth inequality, around 69% can be attributed to those between type inequality that we have generated with inheritances. This is, inheritances can explain, generating this type, around 69% of total wealth inequality in Spain. This ratio descends a bit to 65% for financial wealth, and then ascends to 76% for real estates. The remaining up to the 100 can be explained by other factors that we are not controlling, for instance, race or the place in which individuals are born, other circumstances, and then efforts, right, that we cannot measure. We find that both levels in Spain and in the United States are remarkably high, while in Canada and Italy, the levels are relatively low at around 40%, which is remarkable, but not that high as in the other 2. Although in Canada, we find that financial wealth inequality, it's around 57%, can be explained by these inheritances, by these types we have generated. So some comments. I have already mentioned the ratios, so I'm not going to stop in there. And we know that we have found that financial wealth is particularly affected by inheritances, as this is something that we already knew for the literature. This is something that we confirm. These assets are actually more risky and volatile. So in the end, when individuals receive a request, may reduce the risk aversion to participate in the financial markets, and then are able to, if they can actually get them, higher returns and then accumulate higher levels of wealth. This is something we find in Jordá, this is something we find in Lusardi, and this is something we also find in our paper. However, of course, we know that inheritances are not orthogonal to other factors. They might overlap the effects with the parental education, with race and everything. So how can we try to analyze that? Fortunately, for Italy and the United States, we have information on parental education. So what we do now is we repeat the complete analysis, but not include this circumstance in these 2 countries. And then we apply a Shapley value decomposition that allows us to check the effect of each separate covariate to the aggregate measure. And now we find that in Italy, around 52% of total inequality, remember that previously it was around 40%, now 52% of overall inequality can be explained with these two factors, and the ratios ascend to 61% of financial inequality. And if we apply the Shapley decomposition and check how these variables contribute to these measures, we see that they contribute evenly. Around half is explained by the parental education, and half is explained by the inheritances received. So indeed, we find some overlapping between both factors. More interestingly, even, is the results for the United States. The aggregate inequality of opportunity measures are the same. They are quite similar. It's just a decimal, the change. However, now we find that around 1/3 can actually be attributed to parental education and 2/3 to inheritances. So we have found that, of course, the effect was totally overlapped, and inheritances are a comprehensive variable that they do not only cover the direct transmission of wealth, the intergenerational transmission, but also the opportunities that are provoked, for instance, in this case, by the differences in the parental education, of course, because it gives you, it helps you in your studies later in the labor market and everything. So what is the final part of the paper? What we analyzed is the effect of the inheritances along the wealth distribution. Is the effect of more homogeneous? We are going to check the thesis of Stuckman and Piketty and these guys, that they say that the effect of inheritances should be more important.
About 5 minutes left.
Thank you, Andres, of the wealth distribution. So we check it by using single parameter Gini's, that they are a modification of the traditional Gini index. So they include, just a brief note, they include a V, a parameter V. This parameter V is a parameter of inequality aversion, that the higher gets this parameter, the higher the importance we give to the bottom tail of the wealth distribution to inheritances, right? So let's go directly to the interpretation of these results. These are the plots for the Gini in these 4 countries. In the y-axis, we find the measure of inequality of opportunity, and in the x-axis, we find different values of this inequality aversion parameter. And we find that the more the inequality aversion rises, this is the more we focus on the left part, on the asset poor, the effect of inheritances rapidly decreases towards zero. So inheritances are not that important for the asset poor. They are important for the middle part of the distribution, and of course, to the top part of the distribution. We are thinking about how they define their opportunities. So a clear question should be, okay, what defines the opportunity of individuals, of the asset poor individuals at the bottom of the wealth distribution? So we repeat the complete analysis, but now we implement the parental education. And this is what we find. In the y-axis, again, we have the absolute measure of inequality of opportunity. These are, in the x-axis, several measures of inequality aversion. And now we find that although it actually decreases in Italy, but it does it at a much lower rate than before. And now inequality of opportunity even increases in the United States as we focus on the asset poor. So we find that parental education is actually helpful to explain the different opportunities at the bottom part of the wealth distribution, and on the high part, we have to be focused on inheritances. So what are the main take-home ideas? Inheritances alone are able to explain a remarkable share of overall wealth inequality. However, we have found also that inheritances do not only collect information on the actual transmission, intergenerational wealth transmission, but rather on other factors that condition the opportunities that individuals have to accumulate wealth. And that is important because it allows us to collect information maybe of race. We don't have data for that, but that will be, of course, interesting. Parental education, we have that, the place in which you are born, and everything. So we find that the effect of bequests is particularly strong, particularly important at the top of the wealth distribution, while for the left tail, for the asset poor, the parental education is more important to define the different opportunities. So that will be all. Thank you very much. And all comments, questions, or any miscellaneous, you can find me via email or now. Thank you very much for your attention. And now I'm going to mute me.
Thanks a lot, Pedro, for the presentation. And the perfect timing. You actually had 1 or 2 minutes left, so that's very much appreciated. Usually it's the other way around. I don't see, and it's probably my fault. I must excuse myself. Please enter questions in the Q&A box. You can do this right now, because we don't have any. As I said, that's most likely my fault here. So let me kick off by asking a question. You said you looked at different types of trees, like particularly like standard trees and conditional. I forgot the name. Conditional variable trees, and I was, because they're different in how they are constructed, and say the conditional trees is probably more up to the problem you want to measure. Did this somehow show in your analysis, and can you give us some intuition maybe how different types of trees may actually then lead either to different results, and how we should interpret those? You're muted.
Yeah, I didn't know how to unmute me, sorry. Yeah, you're right. In fact, the first approach I did was with a normal forest, but then I discovered these conditional inference trees forest, and these our main results. I deleted the traditional trees because I don't think they actually fit inequality of opportunity literature. But then Paolo Brunori, the guy a guy working in the inequality of opportunity framework, he found that, I mean, this is the way in which conditional inference trees are done, okay? So first, they test the dependence of this dependent variable, in this case, wealth, condition on the different circumstances. And in this way, they are checking inequality of opportunity. We are analyzing if these particulate covariate inheritances, or if we include other variables such as parental education or race or whatever, are actually important to define this, to condition this dependent variable, in this case wealth, and then they perform the subsequent analysis. So I don't think the first trees are able to they provide similar results, but I don't think they can be accurately interpreted in this framework. But I think they can, precisely because every time we are checking this, we are checking inequality of opportunity in two different groups, because we are checking precisely the distribution of a dependent variable on the circumstances that are supposed to generate that outcome, right? And then in this part, we have the splitting point, in which once we have selected, of course, this split is trivial when we have only one circumstance as the inheritances. So the most important part will be the second one, right? In which we split. So we test every potential split, and then we find that makes the most different groups. The problem here is that, of course, this is highlighted data driven. So if we just run one tree, that might lead to biased results. So one possible solution will be to use bootstraps, which are precisely the forests. So I will go directly for my explanation for these conditional inference trees.
Thanks for the explanation. I just as a follow-up comment, it's probably, I think it would, because inference and storytelling, especially macro, is very important. So I think that's like an very important point to highlight and try to build some stories out of this. So we have some question in the box, and so from Kanya and Miriam. So let's first go with Kanya. You should be able to speak in a moment, and then we go with Miriam. Thanks again.
Oh, hi. I put my question in the chat already, but yeah, I just wanted to know a little bit more about the role that kind of like property stock and real estate plays in kind of explaining differences in kind of the transfer of wealth across generations. Because if you, like, for example, the countries that had high one, I think you said like Spain and the US, and they both have property markets where the houses are like a large part of total assets in the country. Whereas I imagine if property is not a particularly significant asset, then the transfer is automatically reduced, because the main thing that people typically transfer is the houses, right? So I was just wondering if you could explain a little bit more about like how you controlled for properties in general.
I mean, in this paper, I cannot control for that. This is just an accounting exercise, but we have done some research because some referees asked for this part, and we have found that yes, particularly in both South European countries, in Italy and Spain, a relevant part of wealth, particularly from young families below 45 or something like that, is precisely maybe not directly by inheritances, but through gifts. Parents directly gift some part of the wealth price or whatever. So, and this of course will rise the wealth inequality, the inequality of opportunity ratio. And of course, we have found this result also for Canada. The United States, I haven't found any recent work with that, with analyzing this kind of dynamics. Their most recent, I think, was in 2008. So and they were using 2001. So I don't have an explanation for the high ratios in the United States, but that particular wealth transmission and the access to the market credits and everything is particularly strong in Spain. That is something we saw during the Great Recessions, that those households that were left without any houses or whatever were those that were not insured not only by the banks but by their parents, right? So now we have a kind of selection in this group in which, okay, those who were able to maintain their houses were those who actually were inherited it or were able to access the financial markets because they use their parents' wealth to mortgage. And that will be the main.
Yeah, I guess my general point is that in some countries, houses are used as like an extra form as a bank, whereas in some countries, I guess they aren't. Yeah,
exactly.
Yeah, that was it. All right. Yeah, that makes sense. Thanks.
Okay. Thank you. I see that Miriam has asked if I use support vector machine. No, I didn't use these algorithms, and I will definitely explore them. I don't know if they. Yeah.
Should I? Well, the reason is that I mean, tree-based models are good in creating cuts between to group things. Basically in the biggest kind of like where the biggest division is the biggest, but support vector machines are actually even better in that sense because they really try to make the gap between groups as big as possible. So it's a slightly different kind of focus in terms of the algorithm. And I think, I mean, I really like the way what you're doing, and I think it's a really interesting paper, but maybe just to kind of like for completeness, and the referee might, ask you this question is why didn't you use a support vector machine? So maybe you could just try that as well.
Thank you very much. I will definitely look into that. Thank you. I haven't done it so far, but I will do it in a few hours. Thank you very much, Miriam.
Welcome.
So if there are no other questions, we are again perfectly on time. We slightly 1 or 2 minutes even ahead, so which is very much appreciated again. So then let's directly move to our next speaker, Philip from the University of Pennsylvania, and he will talk about give us a little more deeper insight into random forests by its paper "To Bag is to Prune." The floor is yours. Thanks a lot.
Good. Thanks a lot for the introduction. So yeah, I think that actually this is gonna be probably the last talk I'll do with this affiliation because I'm moving as assistant professor at the University of Quebec at Montreal, I guess at the end of the month. But anyway, this is To Bag is to Prune, Phil from the University of Pennsylvania. So what do we mean by this little title here? Really, we're going to talk about random forests, of course, and I'm glad that it came up in the previous talk, so we already have a flavor of it. But really what this is going to be about is to show that the bagging and the other stuff also present in the random forest will have sort of the same impact as if you were to take a tree and prune it. And this is kind of far from trivial. A lot of people think they're quite different thing. And in fact, the paper is sort of going to show that the random forest, why does it work so well? Well, in great part, it's because it's performing its own implicit pruning optimally out of sample. And that's going to explain a lot of a lot of the good outcomes that people get when they apply random forest to many data sets. So anyway, without any further ado, let me make this full screen. That sounds like a better idea. All right. So anyway, I guess it'd be futile to do all of this without having a slightly deeper look at what random forest is before jumping right in. So anyway, random forests, a bit like we talked earlier, they're made out of trees. You can do many things with trees. You can think about inequality. You can think about here inflation. Inflation at time t, can depend on a small tree. Here, the small tree depends on some inflation targeting implementation data and on the output gap. And then, you have your tree structure. So you start with a full sample. Then you ask yourself, is it before or after inflation targeting? If it's after, then inflation is a constant, it's 2% a year, and then it's noise. Or maybe before inflation targeting, it was something more complicated that depended on the sign of the output gap. Anyway, this is a small tree. Random forest is obviously an ensemble of many randomized such trees, and the trees will be deeper. So the one we had a look on the other slide was obviously only 2 layers deep, but really what we're going to do with the trees in a random forest, we're going to grow them really until there is almost nothing left to be fit. So we're going to grow the trees until each of the trees is completely overfitting, and then we're going to put them together in some sophisticated way. But really, it uses this sort of algorithm that is greedy, and really greedy. You're going to hear that term quite a lot over the next 20 minutes. That's the key. It's use a greedy algorithm to build a tree. So it's not like, OLS or neural networks or, anything like that where we, have a function and we optimize it globally. Really, a tree is built in a very different way. It's sort of using this a heuristic algorithm where we do the first, we're here, then we do the fancy problem on the other slide, and it gives us the structure here, but it's never anywhere in the problem, the remote idea that we might have to do this after, right? So that's what we call this a greedy algorithm. It's a myopic way of optimizing the trees. And usually people regard this as a pretty, not a good thing. And this paper is going to actually say, well, it turns out this thing has unsuspected benefits, and these benefits can be huge. But anyway, so we fit the trees with this greedy algorithm, it's important to remember that. And then, we fit one tree, and then, as is kind of well known, a single tree will have high variance and low bias. So what you want to do is put them together. The first thing you do is let the trees run deep. So that's what I already said. You don't want to just stop at 2 layers. You want to really let that thing fit the whole data, and then you have a diversified portfolio of these things. And the way you diversify your portfolio is by bagging. So you fit all these trees on bootstrap samples or subsamples of your data. So you have like a lot of trees are diversified because you fit them on slightly different samples. And there's also this thing called perturbation or decorrelated trees, where when you build your trees and select which variable to split on, you don't include all the variables all the time. And just by doing so, because it's a greedy algorithm, and because where it's going to explore, depends on what it has explored before, just infusing this little bit of randomization here would actually make the trees very, very different. And then, as you might guess, having this, is going to bring a lot of diversification, so it's going to help bringing the variance down. Now, the random forest prediction is a simple average of all these B trees, B being the number of total trees. So anyway, that's like, the random forest crash course, which already took a bit of my time, but hopefully it was useful. Why do we like it? Works very well on a lot of data, even macro data, if you can believe that. And, if you compare that to neural networks, well, random forest sort of works well all the time. It's very hard to build about random forest. And if you think about neural networks, they're fine, but nothing is much harder, much easier, in fact, than to build a terrible neural network. So random forest is sort of a very resilient and robust algorithm. And this paper is about finding out, why it's happening. So I started with this actually very interesting observation. That's a bunch of algorithms fitting a bunch of shell data. It's just a standard data set in machine learning. And what I'm comparing here is the R-square you get on the test sample, so out of sample, and the R-square you get on the training sample, so the data you already seen. And obviously, if you think about it, optimally tuned standard algorithm, and the way we think about this in econometrics, it's going to give you approximately the same performance in and out of sample. If you think about lasso and you have to tune the lambda, obviously the error in sample, when you optimally tune the lambda, will look very much, will have the same magnitude as the error out of sample. If the error in sample is much smaller than when you actually get out of sample, it probably means that you should increase your lambda because you were too lenient on overfitting in sample. So really the action of tuning the model in standard statistical algorithm usually brings the R-square test and the R-square train to be usually close to one another. Of course, the R-square train, so the blue thing, will always be a bit higher, but usually they're in the in the same neighborhood. So that's what we find for lasso, tree, boosting, Mars. Mars is multivariate adaptive regression spline. It's an old model from the 90s. Then you have a deep neural network, which also abide by this principle. But then, look at this. Random forest has this R-square in sample that is close to 1, complete overfitting. And then out of sample, it's still very good. So, it's quite surprising. We have these algorithms, usually when they're optimally tuned, you get these sort of equivalence between the R-squares. But then for random forest, even though there's this huge gap, the random forest doesn't seem to suffer in any way from it. And it's in fact the best model for this data set. So that's the first observation. We really want to, so first we want to explain the success of random forest, and we're going to keep this figure in mind as a guiding light to get there, okay? And there are many explanations, attempts at explanation for random forest success. I'm going to skip this because I guess you really have to know the literature to appreciate all that, and we have limited time. But I guess the argument that people might have heard is that, it's sort of model averaging, and that model averaging is good at decreasing variance. But really, here, it's actually quite a different beast, because if you were to do model averaging and you think about this the same way you think about linear models, model averaging brings variance down, but it should in fact imply that the R-square in the test sample looks like the R-square in the training sample. Why? Because you can show that model averaging, at least for standard linear models or globally optimized model, usually it looks a bit like ridge regularization, and there are papers that show that. And, if you do ridge regularization, it's a bit like the last on the other slide, then you get this sort of equivalence. And clearly random forest is breaking that to pieces. So something else must be at work. I mean, in the paper, which by the way is available on arXiv, I discuss all of these in more detail, but that's the key one, I guess, that we want to show. That's probably not appropriate, but there's a bunch of other explanations which are not, I don't find so compelling either. Anyway, so here they were. Now, what are we going to do? We're going to explain where the puzzle comes from. And it's going to come in, two main points. The first one is what happens in the overfitting zone stays in the overfitting zone. I'm going to repeat that a couple of times. And then the other thing I'm going to say is that bagging and perturbation as an approximation to population sampling, and we're going to be clear about that later, it's really going to help in making sure that everything that is in fact overfitting washes away, so averages out. So, each one of them in isolation is not going to do the trick. If you put them together, you can actually show the random forest can never be too deep or too overfitted. In fact, it's sort of perform its own self-pruning. And that's why when you apply it to whatever, it's very hard to fail, because it actually deals with the tuning itself. Now, it turns out that the sort of conjectures that we're going to develop in theory is going to be saying, well, it's a feature of randomized greedy algorithms. So random forests or tree-based models are not the only greedy algorithms out there. You can think about boosting, like boosted trees, or you can think about Mars. And what I'm going to do is say, okay, we're going to take these insights literally, and we're just going to run with them and build new randomized beauty algorithm and look if those algorithms inherit the same nice properties as random forests, meaning that they won't overfit. They will perform their own optimal self-pruning. And it turns out that they do. And we're going to see that in simulations and in real data. And now, if time allows, well, time won't allow, so let's not even talk about that. So the key here is that greed is good. You might remember that from the Oliver Stone movie, but the key here is a bit different. The greedy algorithm treats what has happened, so what you already have fitted, as given, and what comes next, so what you're going to fit next when you build your model recursively, as if it will never happen. So in terms of optimization, that's the old song is telling you that's not good. It's the inevitable but suboptimal practical approach in the face of computational adversity. And as I didn't say that, this is coming from the Bible on machine learning and elements of statistical learning. And I mean, the reason why it's bad is there's no guarantee to get the optimal tree when you fit a single one. Now, the new song is by building recursively a model of increasing complexity when the true complexity is unknown, when the stopping point is unknown, when is estimated in early step, that's the key, is immune to the pollution brought later by the later step. So you start building your model, you start very simple, and then you add stuff, and then there's a point where you should stop adding stuff. That's S star. And then after that, you start adding things you shouldn't add. And now in a linear model, all of these things are mixed up together because you estimate one model in one swift blow. But in this model here, where we do things one after the other, what you estimated before S star doesn't depend in any way on what you're going to estimate after that. And it means that it's not going to be damaged by something too complex you might be doing later in the model building phase. And really, I mean, yeah, that's what it is. So you have, if you look at this example here, you could fit this linear model. So, this looks quite familiar. You could fit this by OLS. We all know that. So you fit, you estimate this thing in one swift blow. But then if the only coefficient you should have been estimating is beta 1 and beta 2 and beta 3, and in fact useless because x2 and x3 are not related to y, then you're still going to inflate variance by including those because they're all, just together, right? That's just the way OLS works. If we remember the formula, you have the variance of the shocks, and then it's divided by n minus the number of regressors. So if you include useless regressors, it's going to blow it up. But greedy optimization works sort of differently, different steps, step 1, step 2, step 3. If you estimate this first, you have to realize that beta 1, when you estimated this, you estimated beta 1, but there was no beta 2 and beta 3 in that estimation. You estimated this as if that was, the model and that was it. And just by doing that, well, it's, some magic happens because really when you estimated this, then this was completely efficient. This was the OLS with only the regressor that matters. And then you realize that moving from S1, step 1 to step 2 to step 3, then it's not going to alter in any way what came before, right? Because beta 1 is estimated, then you bring beta 2 on top of it, but beta 1 is not revisited. So beta 1 was estimated in a much more friendly environment than OLS mixed up with other things. Now you might think, well, it's only 3 regressors, but this can just be a toy analogy to a high-dimensional model. Let's say we have only 5 observations, then estimating with 1 regressor rather than 3 is going to make a huge difference. Okay, so really that's the key here, is that these betas or 3 split estimated before S star, and S star here was happening between step 1 and step 2 in my example. They cannot be revoked, and the predictor structure attached to them cannot be weakened by adding step after that that are going to lead to overfitting. And I like this little diagram here. That's the Titanic. You probably remember that. And really, that's the key. You estimate the model, you add stuff. If your algorithm is greedy and you add bad stuff past S star, well, the boat stays afloat. And if you go global optimization, you just estimate everything together, OLS style or neural network style, well, the bad stuff past S star is going to percolate past, your S star here and do the good stuff. And then, you know, what happens? Well, you sink to the bottom of the Atlantic. Now, a less maritime example is to look at the tree. Really, that's what it is, right? These are our steps before S star. We estimate this, we get that, and we never think about doing this.
5 minutes left. Thank you.
Good, thanks, Andres. So you never think about doing this, but you did that already, and this is sort of immune to what you're going to do here, right? This is estimated without even thinking this is going to come. So that's the first key point, right? So what you estimated before S star is not reevaluated. Now, what you want to know is, okay, but what happened after S star, all that stuff here, will it average out efficiently, right? Will it average out to, is if I had just stopped here, you know, if I got a phone call from God and he tells me, you got to stop the algorithm here, you know, you're done. Well, the question is, will fitting that and averaging it, you know, through all this bagging stuff will give me the same thing as if I had optimally stopped at the unknown S star? And the answer is yes. And I'm sort of going to skip that to have time to show you a bit of numbers here. But really, that's what's going to happen. You can show that once you reach the point of overfitting, so when you reach the point of overfitting, the DGP looks like this. You know, you're in your node, you're in your true terminal node, and really it looks like, well, you're fitting Y and it's a constant plus noise. And you can show that when you fit a completely overfitting random forest on that DGP, which is what you actually get at S star, then it says you're going to get something that you can just rearrange to show that is exactly the simple mean. So it's, in fact, you can show that the streeting, when it's fitting pure noise and you average it, then and if you rearrange it, you're going to find out that out of sample, it is exactly the same thing as the simple mean. And the simple mean is the best estimator you can get for this DGP, right? I think we're in agreement here. So that's what I discussed in the paper. So you put these two things together. Once you reach the optimal point, the averaging makes it that the prediction is exactly the same thing as if you had stopped at that point. And then what you did before that is immune to what you're going to do next. So it's not impacted by other bad new parameters you're adding. So you put these two things together, and what you get is that random forest quite nicely is really optimally early stopping the procedure, right, out of sample without you even thinking about tuning anything. Okay, so that's the key. Now let's agree to all that. But what I do next, I say, okay, well, the argument is about greedy algorithms and randomization. There are other greedy algorithms out there. There are other randomization schemes. Let's see if this holds up, right? And I do that with boosting, and then when you put that with bagging, it's called booging. And Macroeconomics, because we're going to just shake Mars a little bit. So some simulation results, and I'm going to close on that. And I'm going to leave empirical results for another day. But I think, you know, everything in this, you know, this picture says it all, okay? So the columns are different DGPs. The rows are different base learners. So card means, you know, that looks like, you know, we're fitting trees. This is boosting, so we're fitting one trees one after the other. Mars is just a bunch of fancy polynomial, okay? The x-axis is an increasing index of complexity. So when you think about the tree, it's the depth of the tree. When you think about boosting, that's the number of things you add. And Mars, that's the same thing, number of items you're adding, okay? And then we have different curves, which represent the R-squared between what you get out of sample and your optimal prediction, which I know here is simulation, so the true conditional mean. So a typical curve in this environment, right? We're gonna see the bias variance trade-off happening. So the curve is gonna go up because bias is going down, but at some point complexity becomes too high, and then variance takes over and it brings down your performance again. And that's what we see for the green line, which are plain cards or plain boosting or plain Mars. And here it's pretty clear. It goes up and then it goes down. And then as a machine learner or a data scientist, what you need to do is stop there. But you don't know that ex ante, right? And that can create a lot of problems, especially in tough environment like, you know, macro data. And then you get that, you know, for all the green lines. It goes up, then it goes down. That's just the bias and variance trade-off. And then the purpose of tuning by cross-validation is to stop it there, but you don't know that point. And in fact, finding that point is often tricky. Now, the orange line, so perturb and bag, and then the purple line, population sampling. Perturb and bag is like what random forest is doing. And when you take the green line and you randomize it, and it's a greedy algorithm, look what happened. Then that thing goes up and it never goes down. So you don't need to choose the optimal complexity. You don't need to stop at an optimal point. You can go all the way up to R squared train equal to 1, and then the performance still out of sample, this is out of sample, it's never going to suffer from it. It almost never goes down. So that's for plain random forest models. And then for boosting models, it also doesn't go down, right? I mean, it's not as perfect. And I say in the paper, it's because randomization is not as efficient in those models, but still it almost doesn't go down. And the purple line is the optimal theoretical randomized greedy algorithm. So rather than using perturbation in the model phase and bagging, what I use is population sampling. So I fit greedy algorithms on different data, really like of a bigger population. And that means that you cannot get better than a purple line. So you see that indeed, when you get the purple line, it never ever goes back down. That's the theoretical prediction. But what is quite striking is when it comes to trees, the empirical replica of that, which is the perturb and bag version, like it's completely parallel. So you get exactly the same behavior. So really so it's kind of nice. So if you're in a low noise environment, you don't want to decrease model complexity, because if you decrease it, you're going to increase bias. If you're in a high noise environment, usually you would need to decrease model complexity to make sure you're not overfitting and bringing variance. But here, random forest, you don't need to do that. You can still fit a model with an R square in sample of 1, and out of sample is going to behave nicely. Why? Because we see that the curve here never goes down, as usually happens with the bias and variance trade-off. So anyway, I do that with real data. I show that the phenomenon happens with real data. What do I show is that the tuned versions are the same, give similar performance.
Over, I just wanted to mention.
Oh yeah, don't worry, that's the last one, okay? And then you just get the tuned model is the same as the randomized one that is not tuned. So obviously that's sort of convenient data, blah, blah, blah. Anyway, so we have this key observation that R squared test and R squared train are quite similar usually, but they're not for random forest. I sort of explained that through this new explanation that focus on the fact that we're fitting a greedy algorithm. And even though it's in the background, it turns out it has a huge impact on results. And obviously there's many more details in the paper, and that's it. Thanks for attending.
Thanks, Philip, for the presentation, and congrats to the new job. It will be great. And looking forward to more exciting work, so to say. So please, again, I said questions in the Q&A box, because I don't see any at the moment. So what I wanted to ask is it, say, intuitively, I think that's what you mean by saying fit it first and then not touched on any more in between the levels of the random forest. So is this property of the random forest and the, say, boosting and the effect, say the bagging and then the equivalence to pruning due to it being like a discrete model? Or do you think we could probably also theoretically better understand, maybe in a future paper, and extend these ideas to other models? And I think there should be an analogy here, because all of these models like machine learning, random forest and neural networks are kind of universal function approximators. So at the end, they should somehow, with like a large sample size, converge to the right thing. And just your thoughts on this.
No, that's a good question. I would tend to think not for now, and the reason is the following. It really depends on how they are optimized and how the models are built. So, of course, statistically, if you look at it, if you look at it the standard way, so you think about consistency, you're like, okay, everything you know, this is all non-parametrics, and there are different ways of doing non-parametrics. But here I think that the key is that, you know, if you think about neural networks, you are optimizing a fixed structure, right? You say, you know, this is the number of layers, this is the number of neurons, you know, so on and so forth. And then you optimize that, right? But here we're sort of in a different environment where we're recursively, as we optimize the model, also increasing its complexity, right? Whereas when you think about Ridge, or you think about Lasso, or you know, any non-greedy method like neural networks, if complexity is fixed, and then you just get the structure by running some optimization algorithm. Here I'm really saying that greedy optimization seems to have a very different properties when you randomize it, because also model complexity moves as you optimize it. So maybe if I had to think about this more theoretically, maybe it's a feature of, you know, if you remember the Friedman paper at the beginning of 2000s, it's a feature of model where you do this gradient thing in the function space. You know, if I had to think about this, that's where I would go. But for now, I really tend to think it really depends on which optimization you're running, and when complexity is going up as you optimize, then you get a very different behavior, which, you know, is the one being described here.
Okay, thanks. Yeah, could be. My guess would be I mean, I could be greediness, as you said, the optimization. I would also think of the discrete versus continuous structure of models. We don't have any other questions, so I want to put in another one and maybe give you 1 or 2 minutes to, if you want to show your empirical results. Are your results related to the independence of different variables, like in the input data set? I mean, because this was something which I thought may have an impact on like how, because it may create vertical dependence in the forest, for example, between different samples.
I mean, yeah, I mean, no, it doesn't really depend on that. So do you mean like, you know, like time series dependence or things like that?
No, just when two variables are dependent, because some kind of collinearity in the data set.
Oh, yeah, okay. No, I mean, actually, in my experience, even when you have like this sort of factor structure, right, this is just another way of looking at it. That's how we like to think about it with macro data. Actually, usually it helps. The reason is you have a lot of variables that are sort of similar, but not perfectly similar either. And then you know, it sort of helps for randomization. In fact, when I implement my new greedy algorithms, booging and Marsquig, where you sort of get this phenomenon, I actually create noisy replicas of the data, which are, you know, obviously very correlated with the original data, and it helps sort of bringing randomization in environments where you don't have so many regressors. So it sort of brings back the factor model structure. So I think what really matters is having enough regressors so that randomization kicks in. If you have only one, it's pretty hard to do perturbation, right? So really, if you have 5, and then you can create like noisy replicas, and, you know, it's sort of that, in my experience, sort of helps. So I don't think the independence property here really, I didn't see it playing a huge role. So that's what I know.
Okay, I'm just asking because it's usually also in much of these algorithms assumed for all kinds of theoretical results. So it was just something coming to my mind.
Mm-hmm. Good, thank you.
Okay, so we are almost probably a minute or less to the next presentation. So I would ask Pedro to take over from me to time myself. And you can also introduce me. I can also introduce myself.
Yes, no, it's okay. Well, I am the chair of the chair, which is sort of a chair squared. So now Andreas Joseph will present his paper, and then it's again 20 minutes. I will tell you when you are 5 minutes left, and then you can answer the questions, please, again in the Q&A box. So let's go. The screen is yours.
Thanks a lot, Pedro, for the introduction. Let's see if I get it right myself. So can you see this?
Yes. Go ahead.
Thanks. So thanks everyone for holding on to this session and for joining in the first place on the macro machine learning session. So today we're talking about some recent work we're doing at the Bank of England together with people at King's College London and the ECB on inflation forecasting. And from bottom up here already implies that there's probably some micro data involved here. So as said, I'm from the Bank of England, and let's work together with Galina, Eleni, and George. And for completeness, I say that I speak for myself and not for any of the institutions we are working on, especially the policy institution. So introduction, so quick motivation. I think I probably don't need so much here why this is interesting, or why it's especially relevant for the kind of institution I'm working for. So inflation forecast is one of the main key macroeconomic variables, especially for central bank, is the heart of the decision-making process. What either like expectations, but also forecast of inflations are. But it's also very important for businesses, for example, on their pricing and wage decisions. And in part, is our work, for example, in the advanced analytics divisions, but more generally, central banks and similar institutions, statistical offices are using more and more granular data to assess either inflation or many other indicators. And this comes also hand in hand with kind of technological advances in computing and modeling and other related models which are being used, like say development in this direction, factor models, nonlinear models, and machine learning, which we are contributing partly here, even though we look at, as you see, at many other models. So what we do is we forecast UK CPI inflation, where we look at headline inflation is basically the most comprehensive inflation measure, core inflation, where some volatile components of food and energy prices have been removed, and service inflation, which is again a subcomponent of core inflation. And we do this using monthly item level consumer price indices. I show you in a moment what this exactly means. It's like a couple of hundred of them, and they constitute basically prices. And we also mix this with macro data. And we then do basically like a multidimensional horse race and looking at different models, specifications, terms of we get to kind of tackle this problem. So we look at dimensional reduction, like dynamic factor models and all things based on PCA or partially squared shrinkage, different shrinkage methods, and then sets of machine learning models. And one main contribution here of the paper is also that we extensively look into kind of the black box critique and make a small methodological contribution, how you can either communicate machine learning models more generally, but also especially models in a high dimension settle, because there's an argument to be made that, say, with very granular and high dimensional data, any model is a black box at a certain point, because you cannot explain, say, more than 10 variables, not to speak of hundreds of thousands of variables. So then we use our approach also to make this communication more straightforward. And this is then based, as we already saw, part of it on model decomposition based on Shapley values, and then some reaggregation in inference. So this is, of course, part of a small part of a very vast literature, macro or general forecasting, which where we see developments going, I would say, from the top to the bottom. We see some references here, say, over dynamic factor models, which is still very much state of the art and also used. Machine learning, which is more new to the new to the pack, and I think there's a lot of interesting research questions which still need to be answered, how they compare in different situations to more traditional models. And then also coming into the mix is kind of more granular data, be it prices or others. So what is the data setup? So as I already mentioned, we forecast monthly UK inflation measures, where we look at forecasting horizons between 1 and 12 months ahead. We use two at least 2 sets of data. So the main data set, which enters our models, which also we want to evaluate the forecast performance, are so-called item level indices, which I describe in a moment what this exactly means, which we use about 600. We have many more of them over the total. I must say here also, thanks to the ONS to providing this data, because that's really like a very rich data source and not by far not available everywhere with this kind of ease of access. Then we look also at a larger set of macroeconomic variables. What turned out to be very important is to make proper transformation like chain linking and year-on-year differences, especially for our micro series, to make these models work very well. So the sample period we're looking here is about 10 years. Explicitly no, say, COVID analysis yet, because especially when we look at price dynamics and micro price data, people familiar with this kind of properties notice it's a very complex issue during COVID, because not all prices have been necessarily been available straightforward or are comparable to past prices. So there's a lot of questions being raised here by extending this analysis. So we explicitly stop at the end, say, of 2019. And we do kind of standard time series cross-validation, mostly expanding window horizon testing. And we have a couple of also standard benchmark to evaluate forecasting performance, like an ARP, dynamic factor models, or PCA regression. So a little bit more information on the microdata, which is like a key component of the analysis. So we start with a sample of about 700 series, and then at the end we basically stick to series which we have available over the whole time horizon, which are about 600 of them, which then cover on average more than 80% of the CPI index, which we think is like more than, say, enough for more than good kind of coverage of the overall index to make proper inference on our results, and for example, to feed into policy discussions. So when I talk about item level data and then different, say, aggregation or the index, it's interesting probably to know what this actually means. So when you go into like a shop, you see something like a Royal Gala, for example, Apple or Pink Lady, and your shop may be of a certain type, say big or small in a certain region. And basically this kind of price data are collected by the ONS and then aggregated to item prices in say certain shop for certain products, shop types in a region, and then we get one index basically out, for example, for apples in a certain point in time, which is then like a national indicator, and you get them for kind of many things. So then there's this classification of individual consumption according to purpose, or ESCoE, which basically then which is like an internationally agreed framework, which allows to have different granularity of price indices, starting from the items going up to the highest one level of the aggregate indices like CPI or CPIH, which includes some more items related to housing. But on the other hand, when we communicate results, we, for example, cannot really talk about items because it may be very noisy and uninformative and just too many. But for example, we can talk about more tangible categories like divisions, which, for example, food and alcoholic beverages. And part of the analysis is like showing you how you go from the very granular, then potentially good forecasting performance somehow to a meso level for communication of your results, taking kind of the black box properties of these models into account. So just to give you an overview, if you just plot some of these data, so I think here we already normalized them, mean variance normalized them, say you see really what kind of richness is there in terms of different dynamics, but also items. These are just some examples from the food category. We saw like different types of bread, garlic bread, we go over fruits, different kinds of meats, fish, and so on. You see that's really, really granular information, and we're basically trying to fish for some information there, but of course without doing kind of data mining exercise, but really see what's kind of robust. So that's like an overview of our data selection, which basically It's just a more detailed, as I told you before. It's like in this analysis, we focus on all series which are available during this kind of 10-year time periods, and we cover with this kind of selection about 84%. Currently, we're looking at extension because we got access to a data set which is actually far longer than the original one, and we're now switching basically to another data framework, which also takes kind of the changing decomposition of the CPI index itself, or the CPI basket into account. So now, how do this micro data actually look like? I would say it's very typical of microdata. So, and it is also similar to micro price data in other countries, which often they, like microdata, they have a very large and wide distribution. And for price data, we know that they have this so-called leptokurtic distribution, which is very peaky at the mean, and then with like very wide tails. But something already quite promising is that we see that the mean of our kind of transformed index data and the actual aggregated mean looks kind of similar, which gives quite some hope. But on the other, I also want to mention that probably, say, dealing and transforming microdata had been really crucial here. How to see this? Like I show you here more the same picture as before, just on including the time dimension. And what you see on the lower part is basically the actual CPI together with kind of year-on-year changes, chained indices where you see the mean and the median, which kind of co-move very much with the aggregate index. So that means that's quite good. But if you only look at the raw data, and for example, at the standard deviation of the raw data, which is here the purple line, we see a lot of more and higher noise, but also a lot of seasonality. This means kind of properly thinking about how to work with this data is really crucial to the success of this exercise. So then we have a standard forecasting framework. We basically have different forms of specification, looking at kind of these different types of model where we forecast our target UK inflation over horizon H, looking at, say, these are either kind of our item series or item and macro data, or only macro data, and then some legs of the target variable. So let's come to the results. So what I show you here basically is for headline inflation relative to the ARP model benchmark. This means that's basically the relative root mean squared error compared to the ARP, and this means if it's bigger than smaller than 1, then the model here on the left for a certain horizon is better, and if it's kind of bold with some stars on it, then the forecasts are better. And in this kind of specification, because this was what we also want to investigate in the first place, we look at what's the added value for adding microdata relative to the benchmark for different models, and we see that there are really sizable gains here compared to the ARP, and this can be, say, of the order, say, between 50 and 60% for many models, especially more so on longer horizon, and which is really, really sizable in a forecasting exercise. And we now see that the best performing models are often kind of the dimensionality reduction techniques. This means that dealing with high dimensionality of the problem is really crucial here. On the other hand, we see then also substantial performance again, especially on longer horizon for the kind of what we say more classical machine learning models. And we haven't really been disappointed about this, because nowadays many papers using machine learning say will show you something where machine learning is best. Here it's I think we make an argument of really dealing effectively, for example, in terms of regularization with this high dimensionality is crucial. However, we have a separate work going on which looks at longer time series and, for example, the performance of machine learning models around turning points, and we find that they're really add value here. So I would say this is a little bit of a conditional results where we say that much of our test period here was, I would say, fairly plain and butter in terms of no major crisis going on, while there's a little bit more here to say about relative and absolute performance. So this is the whole thing summarized of our forecasting exercise for all our models and specifications. So this is the ridge which, particularly for the item indices and the kind of shorter sample, performed best. But on the other hand, that's what I wanted to say just with a couple of words before, is that when we look at the neural network, we, for example, were also quite pleased to see that across time and specification, it had a very robust performance with almost equal performance, depending what kind of data you throw in it, while for the ridge, it was more kind of variable. So now, last but not least, okay, we have established that, say, certain types of models with microdata are really good for forecasting in this context here. But we still have this kind of black box critique, and now
5 minutes. Let's, Andreas.
Yeah, thank you. And now here's a more, say, a quite general, say, model agnostic approach, how you can address this either in the machine learning and or the high dimension setting. And the idea is basically already laid out in another paper I wrote some time ago, still working on it. Using basically Shapley values for model inference. And here is kind of a new part about how to deal with high dimensional data. So there's a small recipe, which means basically model decompositions, means basically variable attribution to your predicted value using Shapley values, which is, to my opinion, the most or best justified framework for actually decomposing machine learning models from a theoretical point of view. And then context-specific partial reaggregation, which basically helps you to communicate your results, and then you do some statistical inference on this. So what does this mean? Writing down some simple equations. Basically, what you mean, the first step is model decomposition using Shapley values. Basically, you have some prediction from some observation xt coming, and what you want then is some kind of components phi, which relating to kind of your predictor, which for your observation xt, which tell you how much this variable contributed, and it's, for example, how much did contribute the price change of a white bread, or like a loaf of white bread, to overall inflation. And then you get like a small component to this, and then we have like one step there, but it's of course a lot of many components. And just for definitional purposes, I mean, the Shapley values in a model context are usually defined as kind of the marginal contribution of a certain variable, of having it in the model or not, while going over a lot of potential complexities. That's probably the most challenging part, is here how to exactly evaluate this, but I take this as given here. So I just say this, I know how to do this properly, and then I'm good with the kind of individual item kind of inputs. What I then do for communication, because that's like a decomposition which is linear by construction, I can just do any other linear function on this, and for example, like just a reaggregation to something which I think is valuable. And what we do here is then reaggregation to divisions, which I highlighted before, and I'll show you again at a moment. And what we can then do, because both of these things are linear and have some kind of good properties, we can then do statistical inference on our model components, which basically then allows us to communicate a machine learning model, its output, precisely as we would communicate like a linear model. So some words of to this approach, and the particular problem here at hand, that usually when forecasting we have model differences, that also in a kind of model inference we expect differences, and from a theoretical point of view, these differences are then due to differences in model convergence or the learning process, or whatever individual biases models have kind of achieved, because the data set is too small, basically. And this is a particular problem in high dimension. And but on the other hand, this approach then also allows you to basically explain different performance of the model, but also extract signals. And I think this is very, on the one hand, important to really understand and communicate the results, but also, of course, then insightful. So how at the end does such kind of then the model output, for example, could be communicated is we can say we use two different models. Say we here look only at the blue parts, and for example, headline inflation. Then we could look at some. We have in total 12 divisions. We show the results for 4 here. We could say, for example, well, we can use then a basically almost normal regression table to communicate our like either which is a linear model or machine learning model exactly the same way and see where the models differences are. We see, for example, that for these 4 and this target, the rich regression basically saw kind of signal everywhere, but the random forest saw signal in 3 of kind of the 4 components I'm showing you here. And there's a little bit of more differences for other targets. And then this kind of analysis helps you to dig this out. And I mean, here I just visualize this kind of results, which I think does not really add much to the message. So because I'm running out, so I just go and will wrap up here. So I showed you that micro item level data strongly improve forecast relative to kind of different benchmarks. And overall in this exercise and the test horizon, we found that the rich regression performed best, indicating that really regularization and dealing with high dimensionality is crucial, but many of the other models actually performed similar, and we saw some kind of tentative results that machine learning models are particularly doing well about turning points. And we have actually a separate paper which basically shows that machine learning models are capable of learning economic cycles inherently. And I showed you a model agnostic approach based on Shapley values and regressions to communicate the outputs of either high dimensional or linear models in ways we already know. This means like regression tables. With this, I say thanks a lot. Thanks for being here. Thanks for the chair. Cheers.
Well, thank you, Andreas. The audience can now ask the questions in the questions box. But now, before that, I have a small question, okay, regarding the Shapley decomposition you make. I guess you use the simplest approach, right? The one in which you assume that all possible combinations have the same probability. You haven't tested the nested Shapley or any kind of different Shapleys, right? Just that.
So so for the linear models, you can calculate Shapley values analytically. So you don't need to make any assumptions. Actually, for the tree model, we used the tree Shap because you can also calculate Shapley values kind of more or less analytically or efficient, so to say. For the other models, you would need to use like a background. I mean, that's what I said. There's a lot of potential technicality. You would usually use a background sample and then sample coalitions out there, and then you can assume either that you do this uniformly, or you can do it by other means. What you think is the best way to do it. I mean, if we did this, we did it only by uniform sampling.
Okay, great. Thank you very much, Andreas.
I see there's everybody's overwhelmed, or the explanations have been not very clear.
It has been. I haven't seen nothing else in the box. I mean, I'm supposed to say that we have 3 coffee rooms in which, I mean, the audience can join and ask further questions or continue the conversation. Otherwise, I think we are done, right?
Yes, we can call it at least a session, not yet a day. Then I would say let's just do this and give everybody a couple of minutes back of their life.
Okay. So see you guys. Thank you very much.
Cheers.
And
see ya.